Hello everyone. So now we shall discuss about another FFT algorithm, which is labeled as the decimation in frequency FFT algorithm. So in the previous FFT algorithm, which was decimation in time, which was labeled as decimation in time, it was based on structuring the DFT computations by forming smaller and smaller subsequences of the input sequence x of n. And but here alternatively we can also carry out those decimation operations, that is sampling, upsampling and downsampling in the frequency domain. Okay, but ultimately we should not forget that we want to compute the discrete Fourier transform. So we need to look after that if we are carrying out those decimation operations in frequencies, then to what sequences in the time domain they corresponds to. Okay, so to develop this algorithm, once again we shall restrict our discussion to n, which can be represent which is equal to 2 raised to the power some integer value. Okay, and again we shall compute separately the n by 2 even numbered frequency samples and the n by 2 odd numbered frequency samples. So first of all, let's see that how we can understand them from a block diagram. So since we need to carry out in the decimation operation in the frequency domain, let's say we have this x of k, which is the DFT of finite line sequence x of n, and we shall do the upsample by 2. Here we do the left shift by 1, but note that in the if we are carrying out this shifting operations on the discrete Fourier transform, they are not defined by the regular shifting, so these are the circular shifts, so that you can obtain x of k plus 1. Excuse me, so it was supposed to be the downsampling 2, and the output let's call it x naught k and x1 of k. So this x naught k would be equal to x of 2k, and this x1k would be equal to x of 2k plus 1. Okay, and they are valid for k lying between 0 to n by 2 minus 1. Then for the reconstruction, we shall upsample them by a factor of 2, and the opposite shifting operation, this is circular right shift by 1, and then summing up these two sequences would give you x of k. Okay, this is the overall block diagram where by which we can develop this FFT algorithm. Okay, so now here just to put the point that after this upsampling, these are computed for 0 to n minus 1. Okay, so whenever we do this left shifting operation by one DFT sample, the compressor selects the odd number or the odd index samples. So it is important to remember that the DFT xk is implicitly periodic with period n. Okay, that's why we denoted them as circular left shift and right shift. So if you see the structure of this block diagram, it is almost similar to the block diagram we had seen when we discussed about decimation in time FFT algorithm. So in order to use this block diagram as the basis for computing x of k, we first show that x of 2k and x of 2k plus 1 can be computed from the time domain sequence x of n. Okay, so in the previous module we had seen that the DFT, the discrete Fourier transform, is related to the discrete time Fourier transform by sampling at frequencies 2 pi k by n. Okay, and we had also seen that if n is greater than or equal to the length of the sequence x of n, the inverse DFT yields the original sequence over the same time period, because we had also seen the phenomena of time aliasing while computing the discrete Fourier transforms or the inverse discrete Fourier transform, right? Uh, so the endpoint copies of the xn do not overlap when time aliased with repetition offset capital N. Okay, but here in this figure, what we are seeing that the DFT is compressed by 2, which is equivalent to sampling the discrete time Fourier transform at frequencies 2 pi k by n by 2. Okay, let's write the expression. So the implicit periodic time domain signal represented by x naught k is equal to x of 2k would be a periodic sequence, right? So it would be some x naught tilde of n, which you can write as m is equal to minus infinity to infinity of x of n plus m n by 2 for n lying between minus infinity to infinity, right? So since x of n has length n, only two of the shifted copies of xn overlap in the interval 0 to n by 2 minus 1. So the corresponding sequence x naught of n would be equal to xn plus x of n plus n by 2 for n lying between 0 to n by 2 minus 1. So if you want to visualize this summation, what it indicates, let's say I have some finite length sequence of between 0 to n minus 1. So this xn I am considering, or let me draw this, let's say some okay, so let's consider them 0 to n minus 1. These are the first halves and these are the second half. Since I am considering this between the first half n by 2 minus 1, so I take this as x of n between this interval, and to this I add the next half, right? I am adding the red samples with the green samples in order to obtain this x naught n. Okay, now for the odd index DFT samples, recall that the circularly shift DFT xk plus 1 is basically corresponds to wn raised to the power n of x of n. This we had seen while studying the property of the discrete Fourier transforms. Okay, so therefore the n by 2 point sequence x1n corresponding to x1k equal to 2k plus 1 is in a similar way like we had seen here. So you would have x1 of n is equal to x of n times w of n plus x of n plus n by 2 plus n by 2 for n lying between 0 to n by 2 minus 1. Okay, now using the periodicity property, we would have w, or opening this exponential function, we know that wn of wn raised to the power n by 2 would be equal to minus 1. So we can represent it as x of n minus x of n plus n by 2 times w of n for n lying between 0 to n by 2 minus 1. Now note that here, that while writing this expression, what do we see here? That from this expression, or from these samples, we have subtracted these samples, right? Because here we are considering again the n lying between 0 to n by 2 minus 1. So this is the idea behind computing both the sequences x0 of n and x1 of n. Here we added the red sample, we obtain x0 n by adding these two set of samples, and for computing x1 of n, we obtain by subtracting these two samples multiplied with the circularly shift operator. Okay, so writing the Fourier transforms, it would be x naught of k is equal to 0 to n by 2 minus 1 x of n plus x of n plus n by 2. Again, and for x1, for k 0 to n by 2 minus 1. Okay, so these equations is the n by 2 point DFT of the sequence x naught n. So this one is the x naught and this one is the x1, right? So here we see that the x naught n is obtained by adding the second half of the input sequence to the first half, while the second equation is the n by 2 point DFT of the sequence x1n, which is obtained by subtracting the second half of the input sequence from the first half and multiplying by the resulting sequence by wn. So using these equations, the even numbered and the odd numbered output points of xk can be computed, since we know that x2k is equal to x0 and x2k plus 1 is equal to x1. So if we see the implementation of this by 2 algorithm, this is given by in this way. So here what happens, first of all we compute this sequence, which is x4 plus x0. So this is the first half of the sequence, this is another half of the sequence. So we obtain all these sequences, which is the samples, which is x0. So x0 is obtained by adding this one to this one, and x1 is obtained by subtracting this one from this one multiplied by wn. So these are the input samples to this n by 2 point DFT and the n by 2 point DFT to finally obtain x0 of k and x1 of k, and x0 implicitly are the even numbered samples of the discrete Fourier transform, and x1k from its definition are the odd numbered samples of the discrete Fourier transform. So this is how you can compute the DFT in an efficient way where the amount of computation has been reduced, and the amount of computation in this algorithm also has been reduced to the same amount as we had seen in comparison to the direct computation of the DFTs. Once again, similar to the idea we discussed in the previous FFT algorithm, that we can either go for the further decomposition. So instead of computing, so we can further decompose these n by 2 point DFT to n by 4 point DFTs. So whatever the sequences we have obtained here, so instead of applying the n by 2 point DFT, so these are again the sequences, so we can again decompose it by using the same formulas, and for those we need to compute the n by 4 DFTs, right? And these are the samples we obtain for the discrete Fourier transform. Okay, so the more you decompose, the more reduction in the operation you will achieve, right? So this is the basic idea behind computing the discrete Fourier transform using the decimation in time FFT algorithm. Okay, yeah, so we can close here today.